All right, let's pick it up at problem number 13, letter C. Get my timer started here. Problem number 13, letter C, we have another implicit relationship here. So if I take the derivative using implicit differentiation, the derivative of x squared is 2x, the derivative of y squared is 2y, dy dx, and the derivative of 25 is 0. So I can divide everything by 2 just to make the numbers a little more simple. I'm trying to solve for dy dx, so dy dx would be equal to negative x divided by y. Now that's my first derivative, but they asked me to find the second derivative. So if I find the second derivative, which would be d squared y over dx squared, then I'm going to use the quotient rule, or I can bring the y up and make it to the negative 1 power and use the product. I'm just going to go ahead with the quotient. So I'll have down, d up, minus up, d down, and the derivative of y is dy dx, over down, down. So that would give me negative y because in my work over here, I already know the value of dy dx, and that's the trick with finding the second derivative with an implicit relationship. I'm going to replace dy dx with negative x over y. That's really the only big deal when you're finding the derivative implicitly. So when I clean that up, it becomes mostly just algebra, negative x minus x squared over y squared. Now in the numerator, I'm going to get my common denominator of y, and that will give me negative y squared minus x squared over y squared. There are several little tricks going on here, so watch carefully. That's the same thing as negative. I'm factoring a negative out of the numerator and changing the order. So notice again, all I did is I took a negative out of the numerator and I put the x squared in the front, and that's still over y. I'm dividing by y squared. That's y squared over 1, so that's the same thing as multiplying by 1 over y squared. So that's x squared plus y squared with a negative out front over y cubed. Now this is a little trick. It's not really a trick at all, but it's just a substitution. Look at the original equation, and we know the value of x squared plus y squared. It's equal to 25. So what I could do here is I could take the x squared plus y squared out, put 25 in its place, and my answer looks very simple compared to what it could be. So most of this is just algebraic manipulation. The calculus part is right here. When we're finding the derivative of the y, we leave a dy dx, and then the algebra is where we're going to replace the dy dx with what we found it to be. Alright, the radius of a sphere is increasing at a rate. I can already tell that this is a related rate, and they're telling me that the radius increasing, so positive, at a rate. So I need a calculus abbreviation for radius rate. If r represents radius, then what they're telling us is that dr dt, that is the rate at which the radius is changing at 2 feet per minute. How fast? Again, they're asking me a rate, the keyword fast. They're looking for fast volume, so they want us to find, remember the key to success here is being able to read and interpret the problem, find dv dt when the radius is 3 feet. And they're already telling me up front the formula for the volume of a sphere. I know how fast the radius is changing, and I want to know how fast the volume is changing, so I'm going to need to obviously find derivative. So if I find the derivative of the given function, the derivative of v is dv dt, and on the right hand side I'm going to use the power rule. 3 times 4/3 would be 4 pi r squared dr dt, because we're finding the rates with respect to time. I'm looking for dv dt. I know that r is equal to 3, so I have 4 pi, 3 goes in place of r. I know that the radius is changing at a rate of 2 feet per minute. So this is a simple arithmetic problem. dv dt, 3 squared is 9, times 2 is 18, 18 times 4, 272 pi. Our units would be cubic feet because we're measuring volume per minute. And that's a pretty simple related rate problem that I think all of you would be able to handle. 15, maximize, keyword maximize the area of a rectangle. This is an optimization problem. We're trying to maximize the area of a rectangle, so let me draw myself a rectangle. The dimensions are x and y. You can use whatever variables you want. My goal is to maximize the area. So that is going to be my primary equation. So my equation for area is x, y. That's the equation that I want to maximize. I have a perimeter of 24 feet. So if the perimeter is 24 feet, then the perimeter of this rectangle would be 2 x's added to 2 y's, and that's my helper equation. And the reason they give me the helper equation is so I can solve the equation either for x or y and then substitute into the original. If I divide everything by 2, I would get 12 equal to x plus y. I'll solve for y, it doesn't really matter, equal to 12 minus x. I'm going to substitute the 12 minus x in place of y, and I get area is equal to x times 12 minus x. Distributing gives me 12x minus x squared. If we're going to maximize, we need to find the first derivative, and we get 12 minus 2x. We're going to set the derivative equal to 0. So that would give me 12 is equal to 2x. So x is equal to 6. Now if x is equal to 6, I can go back in here to find the value of y. So y is also equal to 6. So I'll maximize the area when I have dimensions that are 6 feet by 6 feet. In other words, whenever this thing is a square. Now remember, to verify that this is a maximum, I can come back to this point, find the second derivative. The second derivative, the derivative of 12 is 0, and the derivative of negative 2x is negative 2. Now I notice that the second derivative is negative. We have a critical number down here, because that's where the derivative is 0. We have a critical number of 6, and since the second derivative is always negative, including at the critical number, then there would be a local maximum occurring, and that's what we were trying to do to maximize. So just reminding you of the second derivative test to verify local max or local min. Number 16, graph that would be graphing it on a calculator, not by hand. Letter B, use the graph of f to estimate the values of c guaranteed by the mean value theorem. In other words, what they're asking you to do is, I don't necessarily know what the graph looks like, but let's just say that at x equal to negative 1 you have this point, and x equal to 2 you have this point. This would be the secant line that goes through your two endpoints. This is like when we talked about the mean value theorem. We talked about it at Thanksgiving, and you're going on a trip to your grandmother's house. The slope of this secant line would represent your average rate of change. So it's not how fast you were going at any given time, it's just over the entire trip, this is how fast you averaged. The mean value theorem says that at least once during that interval your car had to actually travel your average rate of change. So let's say that your average rate of change was 40 miles per hour. Then at some point during the trip, your car had to travel at an instant 40 miles per hour. So what we're looking for is when the slope of a tangent line, let's see if I can estimate it, about there maybe. No, that's off. So when the slope of a tangent line would be the same as the slope of your secant line, so at this value right here. That's kind of what they're asking you to, in part B, to analyze this graphically. Now part C is really the analytical part. And remember what we just said is find the time at which the average rate of change is equal to the instant rate of change. Now the average rate of change is y2 minus y1, good old-fashioned slope. And the instant rate of change is we're going to set the derivative of the function equal to that and to solve. Alright, now we're going to have to calculate the y values that go along with these x values. So you can see I found the y values by substituting negative 1 and 2 in place of the x values in the equation. And I went ahead and did the arithmetic, and I found that the average rate of change, the slope, is 6. I'm going to set that equal to the derivative, and the derivative of this function is 9x squared minus 10x plus 2, and that's 9x squared minus 10x plus 2, 9x squared minus 10x plus 2. I can not divide everything. I was going to say I could divide everything by 2, but I can't. So that would be 9x squared minus 10x, subtracting 6 to the other side, minus 4 equal to 0. Factoring to solve this, 3x, 3x, 4, not sure how this is going to factor out, but factoring this would solve the equation. Let's check this out. And unless I've made an error in my work, this doesn't factor, so you would have to use the quadratic formula or use a calculator to find these values. But whatever they turn out to be, I'm not going to take the time now to find that. Those would be the times at which the average rate of change is equal to the instant rate of change. Now the last thing that you have to check on in the values that you find is to make sure that the values are inside of the given interval. If one of them or both of them is not, then you would have to throw away either the value or values that do not fall inside of that interval. Now if I made an arithmetic error somewhere in this problem and this is factorable, we will certainly talk about that in class. And another way to check out whether or not this is factorable is actually just to check the answers to see if it comes out to be a rational number. So anyway, but that's the procedure how to do the problem, and if you have any questions on that, you can certainly ask me questions.